Okay, in this video we're going to talk about stress, strain, and Young's modulus. Okay, the essentially three equations coming together in one. We'll deal with the maths first, and then we'll look at the physicalities of what they mean. So first of all, stress. So stress is equal to the force over the cross-sectional area of that object. So that's the force over the cross-sectional area. Unfortunately, this is kind of stress is represented by this little sigma sign here. It looks like that in your sheets, and that is something you need to be aware of. It's not obvious that that is stress. But that's just the way it is. Sorry, that's you just got to learn it. So that's stress, and that's force in newtons, area meters squared. Okay, so interestingly enough, where else you might have be thinking, where else have you seen force over an area? Well, you saw it in pressure. Uniquely, stress and pressure share the same unit. That is often a question that does come up. The Newton per meter squared. So, unit of stress is newtons per meter squared, like that. Okay, so next port of call is for the strain equation. So strain is an interesting value because strain is the extension over the original length. Now, be very careful. The original length is always where it started, and the extension is the point of is the difference between the new length and the old length. So if you were wanting an equation that worked out the extension, so extension is essentially the new length minus the length, the original length, and that gives you the extension, the amount by which it's extended. And please bear that in mind, that's the new length altogether minus the original length altogether gives you the extension, total extension. That's quite important that you remember that, and that does come up quite a lot. So strain is quite interesting because if you look very carefully here, you might notice that extension is in meters and length is in meters. So essentially both these units cancel, which means that strain has no unit whatsoever. No unit. Hopefully you can read that. I might just rub that out a little bit. Can't really see that I've written no unit there. No unit. That's a bit better. So no unit whatsoever for that. So, important thing is that strains often come out as decimal numbers. Now you've got to be very, very careful. This is more exam technique than anything else when dealing with strain. It's a common error that comes up. Now strain, because it has no unit, often is represented as a decimal. So you might get something like 0.12 as a strain. And now that essentially it's essentially like a ratio of the extension over the length gives you a number. Now the nice thing about that is it's always can also be represented as a percentage, and that is essentially 12%. So you've got to watch out for strains represented as a percentage because they do come up like that, and that's quite nasty if they do that. Often on graphs you'll see strains represented as percentages. Sometimes they're just as decimals, in which case you don't need to do anything with them. Yeah, that's absolutely fine. But in this case you're going to need to watch out for that. Right, okay, so Young's modulus then. Now Young's modulus, I'm just going to start off with, is equal to ym. It's not that, but it just makes it easier for the start. Now, Young's modulus is equal to stress over strain. So stress is that little sigma over the strain, which is like a little curly E. Sorry, that's just the way strain and stress are represented in your equations, and you do just kind of need to memorize them. So that's stress, that's strain. Now, really unhelpfully as well, Young's modulus is represented by a big capital E. Some of you are going, oh my goodness, physics, I hate it, but it's just the way it is. You just need to remember those are the letters that represent those things. So let's look at this very carefully now. So we've come up with this arrangement, but what's the unit of Young modulus? Well, Young modulus essentially is, if you look, stress. Well, stress has a unit of newtons per meter squared. But strain has no unit. So if you were dividing a unit by no unit, well, you end up with the unit that's there in the first place. So that means the unit of Young modulus is quite nicely the same unit as stress, which is Newton meters per meter, which again shares its unit with pressure and now shares its unit with stress, which is very, very profound and important. So newtons per meter squared. Okay, what is Young modulus? Let's have a look in the next slide. So in this slide right here, we're going to look at Young modulus. So Young modulus is a measure of stiffness. Okay, how stiff a material is, because the greater the Young's modulus, the stiffer a material would be. That essentially comes from the ideas that when you look at the graphs that we're about to show you, stiffness gives you a good idea of what's going on. So let's have a look. First of all, let's rule out that word, because we don't need it anymore. Hopefully you should have written that down in your notes. So if we look at a standard stress strain graph, in fact what I'm going to do just to get you used to it is I'm going to start using the nomenclature we should be using. So stress against strain. And if we have a material that looks like that, and a material that looks like that, now which of these is most stiff? Is it A or B? Well, A is the more stiff one, because what we've got here is for a very large stress, we've got very little extension. So if you imagine a material that when you put loads and loads of force on it, you get very little extension, well, that you would class that as pretty stiff. Whereas B, however, B, for very little force and very little per unit area, gives you lots of extension. So getting lots of extension for very little. So that's going to be a very elastic material and not very stiff at all. So those are two very different materials. So A, very stiff, B, not so stiff. Now if we look at the Young's modulus as an indicator of these, so if we look very carefully at the lines that we've drawn, so you'll see here that the gradient of this line and the gradient of this line are quite different. Obviously the line for B, the value for B will be very low, but the value for A will be very high. And so the gradient in this case on a stress strain graph is the Young modulus. I'll say that again. The stress strain on a stress strain graph, the gradient is the Young modulus. And since the Young modulus is a measure of stiffness, the greater the gradient, the greater the stiffness. And that's very important that you're aware of that as a property. Okay, so if I've got a material now that breaks at the point that we would suggest right there. So if we've got a material that just stops after it's reached the highest stress, the ultimate tensile stress, it just breaks. We'll talk more about that word, ultimate tensile stress. So at a point where it doesn't go any further, it just is elastic all the way up until its breaking point, and then we call this a brittle material. It's brittle because it doesn't enter what we call a plastic region. It only has elastic, it only behaves elastically up to a point, and then it just breaks. Really great example of this is glass. Now you might not think of glass as a very elastic material, but it is technically somewhat elastic up to a certain point. As soon as you reach that point, it doesn't become ductile, it doesn't go into a plastic region, it quite simply just stops and breaks, and essentially this is, as a definition, is a brittle material. Right, so now if we look at a ductile material, it does something slightly different. So instead of just breaking at the elastic limit, we go into lots of other regions. Now it's important that you realise what all these different regions are. So essentially the first point we reach right here is the limit of proportionality. So that's the point in which stress is no longer proportional to strain. A little bit further on from there, sorry, this drawing is getting bad very quickly. Let's try that out and start again. So we get our limit of proportionality, and then we go a little bit further and we get something called the elastic limit. So that's the point in which it will no longer return to this point right here. So if you release the force at that point, it would still return there. It might not be behaving directly proportionally, but it's still behaving elastically. And so it's okay for it to release that load and then essentially return to its original shape. But once we pass that point now, we go through lots of other strange, weird, and wonderful points, essentially called yield points. Now, yield points are essentially where materials extend rapidly for small increases in forces. So we get a yield point there, and then we get something that looks like this, all the way down to the end. Now, the problem with this is what we like to call a ductile material. Now, after that point right there, that point of the elastic limit, past the limit of proportionality, we get first yield point, and then eventually we get we get another yield point later on as well. But the problem we have here is that the yield points aren't really, really important. The problem is that from this point onwards, it's considered to be ductile. Okay, ductile. Now, ductile essentially is just the word we give to something behaving plastically more than anything else. So we've got an elastic region, and then we've got the plastic region where it's been permanently deformed because it's ductile. It's able to be bent and molded into a different shape altogether. I think one of the best definitions of ductile is essentially allowing it to be drawn into a wire, so you get that thinning effect. So really very important for that as a definition. So the idea that something can be drawn into a wire is ductile. So it's entered the plastic region there, and that is very important for you to remember the names. So let's just write that down. So that's plastic. So that's behaving plastically. Back here, this all the way up to that line I've drawn is elastic. Obviously your notes will be a lot neater than mine. So we got a lot of the ideas behind plastic, elastic, ductility, and limits of proportionality, and elastic limits. Most materials have their elastic limit right by the elastic limit by the limit of proportionality. Now, the small discrepancy in it is just worthy of note, but just something to consider. So, with regard to Young's modulus is something we like to call an intrinsic property. Intrinsic essentially means that no matter how much you have, be it just a small little block, be it a massive cube, they have the same Young's modulus. So essentially, the Young's modulus of a material is constant, regardless of the amount. You could have loads, or you could have very little. It would have the same Young modulus. Very important that you remember that. It's an intrinsic property, and it doesn't change regardless of the amount of material that you have. Importantly, one of the most important ways of finding the Young's modulus, we've already mentioned it, but I will just suggest it again. Finding the Young's modulus, your main way, apart from the calculation stress over strain, should be from the stress strain graph, the gradient. Make sure that you take your gradient nowhere near or as far away as possible from that limit of proportionality, because if you even go slightly beyond it, then your gradient starts to include something that's a curve. It's going to really skew your Young's modulus, which in this case should be constant for that material when it's obeying Hooke's law. So very important that you take that into account. Right, some important algebra that we want to go through here. It's very important that you take this in board because we're going to start breaking down the Young modulus equation essentially here. So when we look at the Young modulus equation, E is equal to sigma over the little curly e epsilon. So what we have here is stress over strain. So let's just make sure we're aware of those, stress and strain. Now, it might be in your best interest to realise that obviously stress and strain had their own calculations. Stress, let's just remind ourselves of that one, force over the cross-sectional area, and also the strain being the extension over the original length. Now, real problem here is that actually we would be expected to combine these equations together to make one big massive equation, which really looks kind of ugly when you put it together, and it looks something like this. Let's just see how I'm going to draw this. Let's start with we'll just do that right side. Equals what we have, F over A over X over L. Ugh, that's ugly. We don't like fractions on top of fractions. Painful to look at. So now we've drawn that in as we would expect, then what we end up with is a problem, because we need to be able to rearrange this. So what we're going to do is just take the idea that if we were to have, when we have this fraction on top of a fraction, what we can do is we can put the bottom, if you have a fraction on top, then whatever the bottom number is can go as a times on the bottom. Whatever the bottom on the bottom fraction, whatever the bottom fraction part of is, can go to the top. And so as a result, we get something that looks like this. So F times by L is equal to A times by X. And essentially there what we've done is that the fraction, the bottom part of the fraction that's on the top goes to the bottom, and the bottom part of the fraction on the bottom goes to the top, and that always works, okay? So please bear that in mind as a little algebraic trick that can help you with any number of problems that might come up. It is also important to note that obviously this equation involves 4 terms, including the Young modulus, which you might be asked to work out the Young modulus or the force or the length, original length, based on 3 or 4 of the values, and you'd have to rearrange this equation as well. So you might want to have some practice of rearranging this equation into all of its constituent parts, just to make sure there is no stone unturned. Anyway, so soon you'll be doing an experiment which utilises all of these values, just give you some practice of using them, manipulating them, and put them into a practical aspect, and we'll see how that goes when you come to it. You might want to read up about it in the textbook. It's in there, and the experimental procedures and the finer points of making the experiment go well. And we'll see you in class for any questions you may have. Do write them on your notes, and we'll deal with them as best we can in lesson.